So we learned about differentiation, limits, continuity, everything. And today we'll be learning about tangent, normal, increasing function, decreasing function, Rolle's theorem, mean value theorem. Okay. So these are more important theorems. And I told you the weightage of differentiation, which means the calculus part, I told you the weightage of it. It is around 15 to 16 questions. Like you'll be expecting 13 to 16 questions. So yes, let everyone come. They will start. Okay, just put good morning so that I'll know like who all came. And did you guys see the recorded videos? Are you able to see it now? So are you able to see it now? So yes, good morning, Harshit. So we already told about the weightage. So we'll be starting today differentiation 2, mainly which is about increasing function, decreasing function, and Rolle's theorem, mean value theorem. So did you guys see the recorded videos? Like few of you were asking me the recorded videos. So yes, if you reply, let me start quickly. Yeah, did you guys see the recorded videos? Ma'am, actually, it's okay. So you guys saw the recorded videos. Okay, fine. So let me start. So today we'll be starting from tangent and normal. So tangent and normal. So generally, what does tangent mean? What does normal mean? Suppose if you have a curve, example, you have a curve like this. Okay, so you'll be having a curve or a circle, example, anything, and there is a line which touches the curve at just one point. So if a line touches a curve at just one point, then you say it as a tangent. So a straight line that touches a curve at a given point. Given point means it touches the curve at one particular point. Then you say that straight line as a tangent. And what is normal? Normal is nothing but it is a straight line which is perpendicular to the curve. Okay, so normal is nothing but it's a straight line which is perpendicular to the curve. Okay, and these are the equations of the tangent. Okay, so these are the equation of tangent and these are the equations of normal. And this is the angle between two curves. So for example, you have a curve 1 and you have a curve 2. Okay, so for this function you define it as f of x. And this function you define it as g of x. Okay, so now at this point you'll be having as x1 and x2 because the tangent touches two curves, right? So angle between them will be f1 dash x1 minus g dash x1 plus divided by 1 plus f dash x1 plus g dash x1. So you have seen this formula somewhere, right? It will be like a minus b by 1 plus ab, some tan formula basically. Tan inverse formula, you'll be having this. So this is the angle between two curves and this is the equation of normal and equation of tangent. So in general, you need not worry about equation of normal and equation of tangent. You need not memorize these two formulas because we can just differentiate it and find the answer. Okay, so if we're getting the equation of tangent, basically what you should do, you have to differentiate, right? So equation of tangent is dy by dx, so that you'll get the slope. So this is the slope of the tangent. For example, for getting slope of the normal, what you should do is slope of normal is equal to 1 by dy by dx. Okay, So basically, slope of tangent is inverse of slope of normal. Okay. So are you clear with the tangent and normal? If you are clear, just write clear T. So if you're clear, you can write it as clear T. Okay. Okay. So I just got 2 replies. Others, please reply quickly. Then only I'll be able to understand if you really got the concept or not. Now, what is monotonicity? Monotonicity means nothing. You just tell a function if it is decreasing or increasing. Then that is called monotonicity. Okay. So you have a function. What is the function called? Y is equal to f of x. You have a function and you say the function is increasing over a particular interval. Okay. For example, you have a function. This is your graph. This is your graph, and your graph goes like this. Okay. And this is your x1 and this is your x2. And this is your f of x1 and this is your f of x2. Okay. In this particular interval, f of in a given interval, for each x1 and x2, for every x1 less than x2. So for every x1 should be less than x2, then and f of x1 is less than or equal to f of x2. Then you call the function as increasing function. So let me write it clearly. So you have x1 less than x2, then you say and f of x1 less than or equal to f of x2, you say this as increasing function. Okay. The function is increasing. Okay. Now, otherwise, what is it is when you have a function f of x1, it is strictly less than f of x2. What you call it as? You call it as strictly increasing. Okay. Again, now what about next one? So these all happens in a given interval. Okay. Now, when do you say a function is decreasing? Same way, suppose you have a graph like this, So this is your x1 and this is your x2. And this is your f of x1 and this is your f of x2. Here, x1 is less than x2, but f of x1 is greater than or equal to f of x2. Then you call it as decreasing function. Okay. Otherwise, if f of x1 is strictly greater than f of x2, you call it as strictly decreasing function. So are you clear about the monotonicity? Okay. Are you clear? So are you clear about the monotonicity? So everything happens over the interval. Given interval, it should be increasing or decreasing. So are you clear? So if you're clear, write I clear. Yes, if you're clear, just write I clear. Are you clear about the monotonicity? Okay. So now testing the function if for testing a function for monotonicity. So again, you say like how do you test the function? You say a function is non-decreasing. Non-decreasing means monotonically increasing. Basically, it is not decreasing, which means a function is monotonically increasing if and only if f dash of, you say a function monotonically increasing if and only if f dash of x is greater than or equal to 0. Okay. And you say a function is increasing, strictly increasing, if and only if f dash of x is greater than 0. Okay. Same way, you say a function is non-increasing. Non-increasing means monotonically decreasing. Okay. Okay. So a function is monotonically decreasing if and only if the derivative of it is less than or equal to 0, first derivative. Okay. Same way, a function is strictly decreasing if and only if the f dash of x is less than 0. So you have to just remember the, like, if they ask you monotonicity, you have to take the first derivative and check if it is less than 0 and see. And if they say the function is increasing, you can say that the first derivative is greater than or equal to 0. Okay. So this is monotonicity. And now let's go to the next one. Maxima or minima. So how do you find maxima or minima of a function? So maxima and minima are the largest, maxima means largest, and smallest value of the function within the range or entire domain. So it is the largest or the smallest value of the function in the given range or the entire domain. Okay. They are also known as extrema. So you maxima or minima is also known as extrema. Okay. So you say a function is maxima, local maxima, if f of a is greater than or equal to f of x. You say it is minima if f of a is lesser than or equal to f of x, where a belongs to the particular interval or the range. Okay, that is interval. Okay, a belongs to the range or the interval. So in that interval, you take a point and you take f of a that should be strictly greater than or equal to f of x. Okay. And similarly, another function f of a that should be lesser than or equal to f of x. Most probably they'll be giving you a. Okay. So these are the two formulas. Like, these are the two definitions for local maxima or minima. Okay. Now, first derivative test. Before going to the first derivative test, let me tell you about the like for existence of extrema or maxima, necessary condition. So you have a necessary condition for existence of maxima and minima. So you f of x is your domain. Okay. So f of x is defined. It's a function. It is defined on a domain D. And you have an x naught that belongs to the domain D. Okay. So x naught is extremum. This is necessary condition. You have, for finding the extremum, which is local maxima or minima, you have to check for the necessary condition. So if x naught is extremum, only if f dash of x naught equal to 0 or f dash of x naught does not exist but is continuous at x naught. Okay. So this is a necessary condition for finding the extrema. Okay. So if you have a function, it is defined on the domain D, and you take x naught, any x naught from the domain, then you take first derivative of the function and substitute the x naught in C. If it is equal to 0, you can find the x naught, and that will be, if you substitute and if it is equal to 0, that x naught is your extremum. If it is not equal to 0, or if you cannot find the derivative but it is continuous, then it is also called extremum. So if you cannot find if f dash of x naught does not exist, if it is not differentiable but it is continuous at that point, then you can say it is also an extremum. Okay. So under these two conditions, you say x naught is extremum. Okay. Now let's talk about stationary point. Stationary point. Stationary point, you say a point x naught point x naught is called stationary. When do you call point x naught is stationary? If f dash of x naught equal to 0. Then you say that point is called as stationary point. Okay. Not f dash of x naught, f dash of any x. When you substitute any x and that point turns out to be 0 after differentiation, if you substitute any x in the given domain, then that point is called stationary point. Now let's talk about critical point. So critical point, you have a point x naught and f dash of x naught equal to 0. So either f dash of x naught equal to 0 or does not exist, or the f dash of x naught does not exist, then you say x naught as critical points. So are you clear? Till now, whatever we studied about maxima, necessary condition for extremum, for finding extremum, and we studied about now stationary point and critical point. So are you clear? So if you're clear, just tell me C clear. So these are just definitions. Basically, these are just definitions. Okay. So it's clear. Now let's go to the sufficient condition. So for existence of extremum, necessary condition just now we saw. And now we are seeing about the sufficient condition. For sufficient condition, you have two tests. One is first derivative test, other one is second derivative test. Okay, this is first derivative test. So let f be a function. So you have an open interval in I. Okay, and also f is continuous at the critical point, such that f dash of c is equal to 0. You know that. So here they told you f is your function. It is defined in the open interval I. Then f is continuous at point C. What is C? C is your critical point. Okay. So only when it is critical point, f dash of C is equal to 0. Okay. Now, if f of x changes sign from positive to negative as it increases through positive, then it is known as maximum. Okay. So it changes from positive to negative. So let me draw you a graph. So you have a graph like this. Like this, you have a graph and this is your point. Okay. This is your point. Here it is increasing, right? So it is positive. And here it is decreasing, right? So it is negative. So when it won't be confusing for you if you remember with the graph. So this point is in maximum, right? So this point, it is in maximum. So it is called, the C is called local maxima. F of C is called maximum value. Okay. So here f dash of C changes from positive to negative. So positive to negative, then you have maximum value. Same way, if you draw another graph and you have a point here, so it is decreasing, so it is negative. Here it is increasing, so it is positive, but it is local here, so it is minimum, right? It is below and it is minimum. So you can say that from negative to positive, you get minimum value. So that's what is written here. So if f dash of it changes from negative to positive as x increases. So this x increases, right? This x increases from here to here, from here to here. This is x1, x2. x1 increases from x2. So as x increases at point through the point C. So this is the point C and here this is your point C. Okay, this point is C. So through the point C, then this is called local minima. See, in the point it is below, right? It is just the lowest point. So that is called local minima, and f of c is called minimum value. Okay. Now, if the function doesn't change a sign, for example, what is that is, like you have a function, it is like this continuously, or it is like this continuously, okay, but it goes from x1 to x2, x1 increases, right? The x value increases, here the x value also increases, but it is just down and it is just increasing, and here it is just decreasing, right? So in this case, the sign doesn't change. It is strictly, it is just increasing. It is not increasing and decreasing. And here it is just decreasing, right? So in that case, what we'll do is the sign doesn't change as the x increases. So C is neither local maxima or local minima. So if you understand with diagram, it will be easy for you because it won't be confusing. Just ulta u and normal u. Ulta u is for maximum, normal u is for minimum. So if you remember that, it will be easy for you. So are you clear with the diagrams and this sufficient condition? If you're clear, write D clear. Okay. So many of you answer like it is clear. Now let's go to the second derivative condition. So for second derivative condition to be possible, your function should be differentiable twice at particular C. So you have a function which is defined. You have a function which is defined on the interval 1, interval I. Okay. And now, and it should be differentiable twice. So it should be differentiable twice at C. Okay. You say if C is a point of local maxima, you know what is local maxima? You just studied. So if C is local maxima and f dash of C is equal to 0 and f double dash is less than 0, you can just write it instead of writing in words. If you write as points, it will be very easy for you. So wait, first one, what is the point? For everywhere, suppose this is C is, I'm not writing these conditions, C is local maxima or not. So if f dash of C is equal to 0 and what is the next point? If f double dash of C is less than 0, okay, then what will happen? F of C will be, it will be local maxima. It will be local maximum value. Okay. Same way, second one, F here C is local minima. Okay. So here in second condition, C is local minima. For the conditions of C, just go to the next slide and see. If it is equal to 0 and if f double dash of C is greater than, strictly greater than 0, then you say f of C is local minima, minimum value. Okay. So this is how you say. Now, what happens when both are 0? If f dash of C is equal to 0 and f double dash of C is equal to 0, we cannot say whether whether it is local maxima or minima. So here the test fails. And the first derivative test will give us the value of local maxima and minima. If f dash of C is equal to 0 and f double dash of C is equal to 0, from first derivative test, we can find the local maxima or minima. From this test, we'll be able to say, depending upon whether it changes sign or not, we'll be able to say whether it is local maxima or minima. Are you clear with the second derivative test? If you're clear, write 2 clear, second derivative. Okay. I want everyone to answer in the class, everyone to respond. So it will be more interactive. And even you will have more interest to learn. Okay. Okay, so let's go to the next one. So next one is finding local maxima or minima of functions of parametric functions. So it is not necessary that all your x values will be in the terms of x and all your y values will be in terms of y. It can be in parametric form also. For example, it can be expressed as t, theta, u, anywhere. So sorry, any value. So you have to be like clear with the parametric function values also. So this is your y, which is your function value. For that, how do you define x? X is equal to phi of t. Y is equal to psi of t. Okay. So both these functions, both phi of t and psi of t, both should have second order. They should have derivative up to second order because we have to find the first derivative test and the second derivative test, right? So both should have an order up to 2. Okay. Now, in the given interval, what happens is this phi of t is not equal to 0. So this phi of t should not, and this is your parameter, this phi of t should not be equal to 0. If at the point, how do you define t? T is equal to, if at a point t is equal to t naught, you take a point t naught and your phi dash of t naught is equal to 0, then how do you define? So what are the terms and conditions for this? So before coming to a conclusion, what are the terms and conditions? First condition is your phi of t and psi of t should have at least second derivative. Okay, it should be second differentiable. I have just written second differentiable for you to understand. That's all. And what is the next point? Next point is your phi of t should not be equal to 0. These are the conditions for checking. Okay. Your phi of t should not be equal to 0. What is the third condition? Third condition is you have a point t naught. You have a point t naught such that your phi dash of t naught is equal to 0. So if you have these three, if your parametric form satisfies these three conditions, what you can do? Then we can say if phi of t naught less than 0, then you say it has maximum at t naught. And if phi of t naught greater than 0, you say it is minimum at t naught. Okay. So if phi of t naught is equal to 0, it is maximum or minimum. So only after checking these three conditions, if your parametric function has these three conditions, then only we can go to the next part and check if it is local maxima or local minima. Okay. So are you clear with the parametric functions and the conditions for it? So are you clear? If you're clear, right? P clear. I just got one reply. So another 30 seconds I can wait. So let me see. I need everyone's reply. So let me check how many people are attending. So now I need all 9 replies. Everyone should reply. Okay. I need all the replies. Okay, one more time. So one more time, like what is first? See, now we need not like in for a function, they can give it as sine t. Y is equal to cos t. So this is also a function, but this function is known as a parametric function since it involves t. So even you can write it as sine theta. So this is also a parametric function. If x is equal to sine theta, that is also a parametric function. So given a parametric function, how do you check whether it is maxima or minima? Okay. So how do you check whether it is maxima or minima? That is your question. Okay. For checking that, you have two functions. For this, you have two values. No. So one function, you take it as phi of t. Another function, you take it as psi of t. Both should be both the function, we have to differentiate it twice. So that is your first condition. So for finding local maxima or minima, you have certain conditions for checking the parametric functions itself. So in that first condition is your function should be differentiable twice. Okay, your both the parametric function should be differentiable twice in the given interval. Okay, and now what is the next condition? Next condition is first derivative of psi of t should not be equal to 0. First derivative of phi of t should not be equal to 0. Okay, wow. Now you take a point t naught in the given interval. You have particular interval, no? Any function that will be given, they'll be giving you an interval. You take any point t naught in the particular interval, then what happens is you substitute the t naught in the phi of t value. So in phi of t, you substitute t naught in c, that should be equal to 0. So these are the three conditions for the parametric form. So if you have all these conditions satisfied, then only we can go and check whether phi of t naught less than 0, it is maximum. Phi of t naught greater than 0, it is minimum. Phi of t naught equal to 0, it is neither maximum nor minimum. So cannot be decided. It is open means it cannot be decided. We cannot tell whether it is maximum or minimum. Okay. So Mike, did you note down the conditions because you asked me to show the conditions? And Harshiv, are you clear? So are you please clear? So are you clear? Okay. Now Rolle's theorem. So Rolle's theorem also, instead of learning it as paragraph wise, if you learn it as points, it will be easy for you to remember. And these are very simple tricks to remember. So in exam, if you like anything given as paragraph, it won't be very comfortable to remember. So just remember as 3 points. For Rolle's theorem, first condition for Rolle's theorem. So as you know, like f is a function, and the first condition is f is continuous on the closed interval, a comma b. What is the second one? Second one is, and the function f is differentiable. F should be differentiable on open interval a comma b. Okay. And what is the third one? Then third one is f of a should be equal to f of b. Okay. Such that f of a equal to f of b. So these three conditions should be there. First is f should be continuous on the given closed interval of given interval. So closed means, for example, you take 1, 2. Closed means even 1 and 2 both should be included. Open means when you find the different whether it is differentiable or not, you need not include the 1 and 2. Okay. So first condition, f should be continuous on closed. Second is it should be differentiable on open. Third, f of a equal to f of b. Then you say f dash. This is f dash. Then you say f dash of x equal to 0. Okay. Are you clear? So are you clear with the question? So if you're clear, just write it as clear. And these points are not necessary. Then there exists such that f dash of c is equal to 0. That is important, but this is not necessary. So are you clear? Okay. So now these are the three conditions. Just remember, if these three conditions satisfied, then you say f dash of then there exists interval c such that f dash of c is equal to 0. then you can say that f dash of c is equal to 0. Or this is also same. Both of them are same. Here, instead of this x, I have put c here. That's all. Because c belongs to the interval only. No? Same way here also, this statement and this statement are same. This statement and this statement are same. They are just repeated. So don't get confused. Both are same. Both are the critical points. Okay. Now let's go to the next function. Next is nothing but Lagrange mean value theorem. So for Lagrange mean value theorem, let me write it. You have a function, so which is real valued function. It is f of x, okay? So a real valued function, f of x. So f of x is your real valued function. Now it is defined on interval, closed interval a comma b, okay? And such that it is continuous on closed interval. So again, so f of x is continuous on closed interval a comma b, and it is differentiable. So f of x is differentiable on open interval a comma b. Then you have a point c. C belongs to open interval a comma b. Then you say such that we say f of a minus f of b minus f of a by b minus a is equal to f dash of c. So this is your Lagrange mean value theorem. So the same thing is given here, but these conditions are very important. It should be f should be continuous on closed interval, and f should be differentiable on open interval, and c should belong to open interval. Then you say f of b minus f of a by b minus a is equal to f dash of c. Okay. So are you clear with the Lagrange's theorem? If you're clear, just type L clear. So if you want to copy this one also or this one, anything's fine. But I've written it as points. So it's better to remember as points than paragraph. For everything, you have 3 points. Even for the previous thing, you had 3 points. Even here, you have 3 points. So are you clear?